In this video, we will show the derivation of the complete response of RC and RL circuits. So the response of a circuit is simply its behavior as a result of the application of a voltage or a current source or a combination of those sources. Let's work on the series RC circuit first. So here we have a simple circuit with a switch that closes at t equals 0. Here we want to know the response of the circuit after the switch is closed. Response could mean what is the voltage across the capacitor or the current through the capacitor. It is sometimes convenient to solve first for the voltage across the capacitor for a series RC. To solve this voltage, we still apply Kirchhoff's laws. Since this is a single loop, we don't need the KCL. So here we perform a KVL around the loop. So this is our KVL equation. So the sum of the voltages is equals to 0. By Ohm's law, we can express the voltage across the resistance as IR. And we already know the relationship of the current through a capacitor and its voltage as being this equation. We now replace this one of the voltage across the resistance in terms of this. So what we get is this one. Okay, so it's a differential equation in the variable v sub c. We can rearrange that differential equation and we will get this format. So this is a first order differential equation, and to solve for v sub c, we need to solve this differential equation. So here is the differential equation again. We can rearrange the variables such that it would look like that. So take note that our variables are v sub c and the time t. Now I have rearranged this in this manner so that we can solve the differential equation using separation of variables. So to solve this, what we can do is we integrate the equation, okay? And when we do that, that means we need to integrate this and this one. So the integration of this will give us a natural logarithmic function, while this one is simply a function of time. So that will give us this equation. And we need to introduce a constant after that. So how do we find the constant? Or apply the initial condition for the circuit. So for example, what is the value of v sub c at t equals 0? So let's assume that v sub c at t equals 0 is equal to v sub naught. So applying this initial condition to this equation, that will give us a value of k equals to this one. Then we use this value and replace this k here. That will give us something like this. So this is our new equation. We transfer this term here on the other side. That will give us this equation. And by the property of logarithms, this one can be replaced by this. Okay. So it's a natural logarithm of a quotient. Then we do an anti-logarithmic function in order to express the right side in terms of the exponential function, or we want to get rid of this ln function. So doing that, this equation can be written in this way, okay? And we can solve for v sub c from this equation. So our v sub c will be this one. So take note that v sub c is valid for time from t equals 0 to time infinity. It is not valid for t less than 0. So this is our v sub c again. We can plot that equation, and if we do that, we will get this one. So the voltage starts from an initial value of v sub naught, because that is what we have assumed, that at t equals 0, it is equals to v sub naught. And the voltage will increase to some constant value v sub s over time. So what can we say about this equation and the plot? So first, equation 2 is called the complete response of v sub c of the series RC, because it shows both the steady state component and the transient component of v sub c. The first term is the steady state component of v sub c, so it is a constant. And the second term is what we call the transient component, which is an exponential function of time. So as you can see, uh, this term will approach 0 as t approaches infinity. So this term actually vanishes over time. So as t approaches infinity, v sub c becomes steady state. So meaning it becomes v sub s, which is the applied voltage on the series RC after the switch is closed. Based on equation 2, in this equation, we can say that v sub c technically can never attain a steady state, or can never be equal to v sub s. But in actual practice, we usually consider v sub c to have achieved a steady state after time t equals 5 RC, okay, 5 RC, from the time the switch is closed, assuming that the capacitor has no initial voltage. Well, the time can be lesser if the capacitor already has an initial voltage. We can determine the current through the capacitor, which is this current also. So from the relationship given by this equation, we can get the derivative of v sub c, okay, and that will give us a current that is shown by equation 3. We can plot I, so that is the plot of the current through the capacitor and through the entire circuit as well. This plot and this equation shows that I has only one component, which is a transient component. Thus, I will vanish over time. Take note that upon the closure of the switch, I jumps from 0 to a This value V sub S minus V naught over R, but it decays after that to 0 as t approaches infinity. Let us work on the series RL this time. So again, we're interested to know the voltage across the inductor V sub L, or the current through that inductor. We can apply KVL and produce this equation, but then again we know that V sub R can be expressed in terms of IR, and V sub L is L di dt, where I there is the current through the inductor, which is also our I through the circuit. So we can replace V sub R by this one and V sub L by this one in this equation, and that will give us this equation. And simplifying it, we'll get this format. Using the initial conditions that at t equals 0, the current through the inductor is I sub naught, we will get the solution for I as shown in equation 4. So here is the equation for I again. We can plot that equation, and that will give us this plot. So again, similar to V sub C, I will start um, from a certain value because we assume that at equals 0, I equals I sub naught. And it grows until it reaches a constant value V sub S over R. Similarly, for a series RL, this equation is called the complete response of I because it also shows the steady state and the transient components of I. The first term is the steady state component, and the second term is the transient component. So as t increases, I becomes steady or equal to V sub S over R, where V sub S is the applied voltage to the circuit after the switch is closed. Again, in practice, I is considered steady state after time 5L over R. From the time the switch is closed, assuming that there is no initial current through the inductor at t equals 0. We can also solve for V sub L, the voltage across the inductor, from this relationship, and that will give us this equation. We can plot the voltage, and this will give us this plot here. So this voltage has only one component, which is a transient component. And this voltage also abruptly changes from a 0 value before the switch is closed. It jumps to this value and it starts to decay after that, and goes to 0 as time increases. So in this video, we just showed the derivation of the complete responses of series RC and RL circuits. For the series RC, we solve for the complete response of the voltage across it, and we notice that it has two components, the transient component and the steady state component. Both the voltage and the current of the capacitor undergo a transient period, but will eventually settle to a new steady state condition that will result into a constant voltage and a zero current. For a series RL, the complete response of the inductor current also contains a steady state and transient components. And both the voltage and the current also go through a transient period, but will finally settle to a new steady state condition that will result into a constant current and a zero voltage.